calculate Bohr's orbit. Then expression for velocity Vn. The speed of this expression for speed will be anybody? I think I don't have expression for speed. Okay, I think I'll remember z square, ze square, then what we get, ze square 2 epsilon naught nh. So this again will reduce this everything into Zn by V1. And what is V1? Or C by 139. So something we have simplified it.
C by 136, sir.
136, huh? Yeah.
137, sir.
137, I remember 137. C by 137. Okay, this is one thing, Vn. Then last one, we brought expression for En. Kinetic energy and potential, both we brought it. Let me go for only writing En. So the total energy is given by minus m e to power of 4 z square 8 f naught square h square. Or this in terms of minus 13.6 electron volt, or in terms of Rydberg minus RHC, where Rydberg constant R equal to 1.09 into 10 to the power of 7, that one. I think these are some various forms what we ended up. So I think this everything, I think actually I wrote here, no need to write that. What do you mean by capital R? It's a Rydberg. And for different atomic structures, R will be different. That in the end I'll discuss here, different Rydbergs. It's not there in book much, that one, but in exams can be asked here. For hydrogen atom is what I'm discussing, this Rydberg. The value of Rydberg is for this hydrogen atom only. For different hydrogen-like atom, the value of R will be different. Strictly, this is for hydrogen atom. The value of R, what we have is 1.09 into 10 to the power of 7 meter. Okay, this is about the energy. So let's go for the construction of the energy level diagram. So let's take this one. And now how to calculate the construction of hydrogen atom, will take it. Energy level, oh, it's here. I'll bring it back there. Let's get into the, okay, how to construct this energy level diagram. So we'll first use that formula what we have. En equal to 13.6 electron. We are defining this for hydrogen atom. For hydrogen atom, so what should be the value of z? Z equal to 1. Put n equal to 1, 2, 3, 4, 5. Then we'll get the energy level diagrams. So this will be E1. Minus 13.6 electron volt. For n equal to 2, this is called as 3 point. These values you are supposed to remember. In exams, you will be in comfortable position. I am making things clear. In exam, biggest trouble for you is you must memorize for hydrogen, helium plus, lithium double plus, at least till n equal to 6, because these are the types of numericals what will get it. Till n equal to 6 is what you should remember. There's no other way. In exam, you can save time. Straight away, what happened? You can save time here. minus 0.54, E6 is how much? 0.38, and E7 0.28. Okay, now, so these are the values to that. So now what happened? Bohr's postulate, what it says, like how do that photon will be emitted? How that hydrogen spectrum? What it says that when an this called like a ground state. So these are, I'll give name. I'll call them as this is a ground state. This is called like a first excitation. Don't call second excited. The first excited state. This is the second excited state. This will be third. Like that, what happened? We can give number n equal to 4 will be third excited state. This is the fourth excited state. Like that, you can give the name for them. And n equal to 1. What do you mean n equal to 1? Put n equal to 1 in this formula. Put n equal to 1 in this formula. Then I think everything, oh, yeah. Okay, everything is visible. You check it now. Put n equal to 1. What for hydrogen atom? What is z? Z equal to 1. So, so put z equal to 1. Then n equal to 1, 2, 3, 4, 5, 6, 7. You get the values that you are going to put negative. What do you mean negative? Because it's like a closed orbit. The electrons are going to revolve in a closed orbit. That's why the total energy will be negative. Go back to gravitation chapter. When you get E negative, what does it mean? The total energy of a system negative means it's a closed system. So the electron and the nucleus, they'll form a closed system. That's why the energy we are getting is negative here. This is n equal to 7. So like this, we can some higher level, put n equal to infinity. N equal to infinity will be the first. It should come from here, line. Yeah. So this will be the n equal to infinity. Like this. So now how the Bohr's like a establish this particular thing. So he suggested like how to calculate the wavelength of photon emitted when it makes a transition from one state to another state. So for that, what he suggested is use the formula delta E is equal to the how to predict the wavelength of that particular thing. So H delta E is equal to initial state to final state. When it makes a transition from higher to lower state, then give out a photon. That's called a de-excitation. This should be called as C by lambda. What is EI? According to the formula, EI formula R S C Z square by Ni square. Negative. This will be minus R H C Z square by NF square. HC will get cancelled out, so we'll be end up with only 1 by lambda is equal to R. Z square will be there. So since I'm discussing for Z equal to 1 hydrogen atom, hydrogen spectrum is what I'm explaining. So Ni square minus Nf square. This was the formula. What happened? The board didn't propose. The board just said that when a electron makes a transition from higher to lower orbit, then it will give out a energy in the form of a photon. Pretty sure. You don't know how that formula will come all, because at that time he didn't have much idea about that. The Planck's quantum radiation law, that one. He had that, he knows that one, but he was unable to put it in proper way. He just stopped there only. Next, one of the like a negative of this will be, I'll put it like this. This will be 1 by lambda Next step, I'll simplify. NF square minus NI square. Okay, one math teacher. So one of the math teacher called like Balmer, what happened? He proposed this particular formula, that one. Okay, like this, see, like using Bohr's postulate, you can design a formula. Using that formula, we can explain the hydrogen spectrum. The Bohr could not explain hydro. He just said that as like when it makes a transition, that one, the form, what happened? The math teacher from what happened, Balmer, what happened? He suggested, okay, this particular basic formula. Okay, now we are y delta E is what? Transition, no? EI minus EF, it makes a transition from IA to lower state. You can see from the calculations when I go for that one. Okay, now how to predict the wavelength of any line in hydrogen spectrum? How to predict
Sir,
wavelength of
sir, you missed Z square. R Z square.
Z equal to 1.
Okay, sir.
Z equal to 1. So how to predict the wavelength of any line in this hydrogen spectrum? So what they suggest is like just use this particular basic formulas. Means like I want this is called like a first line of the Lyman series. How to predict the first line? So where is initial? Initial is what? Infinity. Put final NF equal to 1. So you'll get the wavelength of the first line of Lyman series. The first line is what we should call either this or this one. This is called like a series limit, no? This is called like a first line. This is called like a second line, third, fourth, fifth, sixth, seventh, and this will become infinity. We should not call this the first line. This is called like a series limit. This is called like a first line, second line, third line. I think there's a convention they brought it. Because if I call this is first line, I think I can't give name for this one. No? Therefore, they call first line. What is the first line of Lyman series? So when hydrogen atom makes a transition from first excited state to ground state, then first line will come. So we'll calculate the first line. So first line means shall we put lambda to 1? How to calculate lambda to 1? Z square, because I'm describing purely for hydrogen atom. So Z will become equal to 1. Put that also thinks clearly. And this is a ground state. No, what is the initial state? What is the final state? And NF should be equal to 1 square. And initial is what? 2 square. 2, 1. So this will become initial, this will become final. It makes a transition from initial to final, from first excitation to ground state. So what is the first line of Lyman series? This should be R 1 minus 1 by 4. So this will become equal to how much? 3R by 4. Or lambda 2 1 should be equal to 4 by 3R. Now what you should call this? First line similarly, I want the second line. What is the wavelength of second line? It should be, it will make a transition from 3 to 1. 3 to 1. This in exams that they are using this convention rather than giving the wavelength first line of Lyman series. This is similarly expression for second line of how to calculate wavelength of second line of Lyman series. So it should be 3 to 1, not 3 to 2. It will make a transition from 3 to 1. This is called like a lambda 3 1. This is lambda 2 1. What should be the formula? It is making a transition from NF, final state is 1 square, initial is 3 square. So 9, so this will be 8R by 9. So what is lambda 3 1? So like this, the wavelength of any specific line what will happen, we can determine but using this particular formula. Similarly, first line of Balmer's series. First line of Balmer series or first line, it will come in visible region, that means first line of Balmer series means n equal to 3 to n equal to 2. It will make a transition from 3 to 2. First line. What should be the final initial? What will be the final state? Final state. This will be the final state. This was the initial, no? This will become first line. Try to see that this will become first line. So therefore, no, it should be equal to 2 square minus 3 square, or 1 by 4 by 1 by 9. How much it will be? 5 by 36 r. Like this, we can find out the wavelength of any specific line in the hydrogen spectrum using this formula. I think the formula you should remember, because when it is de-exciting means when atom jumps from higher to lower state, it will give out that energy in the form of a photon. Planck's radiation law, he had idea, and the photon from the photoelectric effect, he had idea. The Bohr, he made a postulate. Three postulates are there, very important. One, the electrons, they'll revolve in a circular orbit. There's a thing. Next again, when an electron, when hydrogen atom makes a transition from high to lower orbit, it will give out the energy in the form of a photon. There's a thing. Third postulate, the angular momentum of a revolving electron is like you can say like it's quantized, which is equal to nh by 2 pi, integral multiples of h by 2 pi. These are the three postulates. The second postulate what he has put is this part. The first postulate, with that he derived expression for E and all. Second postulate, he just brought in this particular thing. How to define the hydrogen spectrum. So there's a one method of determining the wavelength of any line in the hydrogen spectrum. Okay, now we'll once again I'll come back. This is called like a series limit of Lyman series. Now, what is the series limit of Balmer series? So this particular line, this called like a first line, this called like a second line, third, fourth, fifth, and this is called like a series limit. Or shall we put shortest wavelength in the Balmer series? This is the shortest. Or this is the shortest. Which one you can put? What do you mean by shortest wavelength? E equal to SC by lambda, where energy is more, lambda less. So shall we take this is the shortest wavelength in Balmer series. Longest wavelength will be this one. Longest wavelength in Lyman series, this one. Shortest wavelength will be this one. From n equal to infinity to n equal to 1 will be the shortest wavelength of Lyman series. Or it is also called like a series limit. I think not possible greater than that. So sorry, lower than that, not possible. They're called like a series limit here. So like this, what happened? The word series limit is brought shortest, longest, first line, second line. These are the different ways of expressing this particular names they're given. Third line of bracket series means what you should do. The transition will take place from n equal to 7 to 4. There's a third line. Fourth line of bracket series means from n equal to 8 to this one. So like this, we can define any number of that particular lines we can determine here. So how many lines will come? I think from n equal to till infinity, no? There's no n for that. So what is the shortest wavelength? From n equal to infinity to n equal to 1 with the shortest wavelength in Lyman series. Longest wavelength will be from 2 to 1 for the Lyman series. So like that, we can define shortest, longest, first line, second line in each particular series. That one. This is called like a Lyman, Balmer, Paston. So when transitions occur from IS state to n equal to 1, Lyman series. Transition occurs from IS state to n equal to Balmer series. Transition occurs from IS state to the second excited state or n equal to 3 is called as a Paston. Like that, the names are given for this one, P fund. So how the in exams, the third line of bracket series, a photon corresponding to third line of bracket series is incident on a metal plate. Third line means of bracket series. N equal to 4 is the bracket series, no? Here. And third line. So you should take it to be n equal to 7. So a photon corresponding to this, what happened will be incident on a metal plate. I think you must be very careful. So if you remember these energy levels, it'll be very easy. Or if not energy, at least this formula, this particular formula. So this is the initial, this will be final, as it just makes a transition from higher to lower state. That higher state is initial, the lower state is will become the final. These are called like a excited state. What do you mean by excited state? Why? Because if at all you fill up a hydrogen gas in a some tube or in a container, leave it. Where do that hydrogen atoms will stay? They'll stay in the ground state. Hydrogen atom. So when you supply energy, what will happen? It'll get excited. So then how much of you should supply? If you supply 10.2 electron volt, then it will undergo transition like this. If you supply 10.2 volt, yes, 10.2 electron, it will jump here. If you supply furthermore 12.03 or something, it will jump to this one. So like that, depending upon the energy received, what happen, the hydrogen atom will get excited. For what time it will stay in this excited state? For 10 to the power of minus 8 seconds. So the hydrogen atom, this data very important. Hydrogen atom stays in an excited state for time for 10 to the power of minus 8 seconds.
Sir, lambda 32 is 36 by 5R.
36 by 5. Huh? Yeah, okay, okay. This one. Look at this one. For what duration of time the hydrogen atom will stay in the excited state? For 10 to the power of minus 8 seconds. It will not stay there only. Suppose if hydrogen atom is in ground state, if you supply energy, it will just jump to 10, that particular first excited or some higher excited state. It will stay there for this much of time. Again, it jump back. When it is moving from high to lower state, it will give out photon. Okay, next question comes. Suppose a hydrogen atom. If it makes a transition from, if it is, I'll give energy, from ground state, it will jump to the fourth excited state. Then how do it will return? Yes, it may return directly from 5 to 1 or 5 to 4, 4 to 1 or 5 to 4, 4 to 3, 3 to 2, 2 to 1. Any of the possibility. Sir, how it is possible? Yes, by only through experiments you can tell, but you cannot tell the hydrogen atom, you, okay, make a jump from 5 to 3, then 2 to 1. No, it depends on, and that we cannot control. The technology what we have, we cannot decide like which hydrogen atom will make transition from where to where. Next you have to ask question, sir, is it all hydrogen atoms same? Yes, here is what the quantum mechanics will come into picture. Why one hydrogen atom? You take two hydrogen atoms, you excite them, both you excite to fourth excited state. Then one hydrogen atom may make transition directly from 5 to 1. Other hydrogen atom will make transition from 5 to 3, 3 to 1. Why do they behave? I think the classical physics what we know or the Newtonian physics what we know, we cannot answer. Through quantum mechanics only we can answer it. This aspect troubled a lot after 19th century, say 19th century, sir, 1900 to 1940. The scientists were troubled. They were in big trouble because everything they wanted to give explanation, because the physics what till now you learned, there was a reason for everything. The first time in this chapter where you are not giving reason, you say that nature behaves like that only, finish over. This particular aspect happened the first time it happened in physics. I think it started from Galileo, the physics. From Galileo we started giving reason for everything. But once this 19th century came, what happened for most of the physics what happened, we are unable to answer. The nature behaves like that only. So now the scientists what happened, they're in a big trouble. So why we are unable to give reason? There should be some mechanism. Even quantum mechanics will not give everything answer. To some extent, it will help us to understand the universe in systematic way. That's all. But we don't have complete answers. So this part of physics is what is troublesome for almost. So then what happened in 1940 or 1930, they made some conclusion. See, like here, things are not like a what we are thinking. So probability will come into picture. Then they carried forward. So especially the 30 years, no, the first 30 years, 1999 to 1930, no, everyone was in confusion because for every 3 4 years the new discoveries, the new inventions came, the new laws came, and little bit contradiction, this that, and the Newtonian physics was not holding good. So they were in a deep trouble because we are building up our physics by Newton physics. All of a sudden I'm asking you, okay, don't think like that, think in new way. And if you start thinking new way, you don't feel, we don't feel matter waves. There are matter waves are there, we never feel matter waves, but matter waves are there. So what to tell to student that don't bother matter waves? So that what happened here. So finally what they made a rule, oh no no, it is something like this, okay, we'll make it. They made a rules and we are proceeding further. Then they were shocking that what will happen to the new modern physics, means the new inventions, the new technology, science and technology, what will happen to that? Will this quantum mechanics or this particular physics what we are now discussing, so how it will trouble? So they made a rules and they moved forward because what all we have today mobile due to quantum mechanics only. I'm making things clear. Without quantum mechanics, there is no semiconductor. Without semiconductor, no transistor. Without transistor, there is no industry. There is no engineering industry. It's over. Everything started with quantum mechanics only. Okay, let's come back to this one. So like this, what happened? The hydrogen spectrum he was able to explain here. Okay, after this, so for hydrogen atom will stay only for this duration of time. This is something where it will not stay there permanently. I know how to excite hydrogen atom. After this, after explaining the hydrogen, the next question comes: how to excite hydrogen atom? How to excite hydrogen atom? So let me begin like this. So what is the minimum energy needed to excite hydrogen atom? I'll draw that basic energy level diagrams.